Carnot showed an important relationship that holds for an ideal engine. This ratio is only good for an ideal engine. It is not valid for real engines, but it does allow us to gain an upper limit on the maximum possible efficiency of heat engines. And here's where that equation we wrote up higher comes in handy now. Let's recall what the efficiency is from above. E is equal to 1 minus QC over QH. That's true for all engines. Doesn't matter what kind. But now, if I have an ideal engine, I can replace the ratio of the heats with the ratio of the temperatures. And that is, for ideal engines, the maximum ceiling efficiency I can get out of any kind of heat engine. Because the steps are done reversibly, which means there are no changes in entropy, then we can write another important relationship that is valid for the Carnot engine, and that is that the change in entropy for one complete cycle in a Carnot engine is equal to 0. These two relationships, for efficiency and for the entropy change, are only true for ideal engines, but they give us a starting point. Let's solve a couple more example problems. What is the maximum possible efficiency of an engine that operates between 500 and 250 degrees C? Let's use the Carnot relationship. We'll need to convert our temperatures to absolute temperatures, and now we substitute the numbers. I find that this particular engine is just over 32% efficient. Let's look at the next problem. The exhaust temperature of a heat engine is 240 degrees C. The engine produces 500 joules of work and has a Carnot efficiency of 45%. A. What's the temperature of the heat source? B. What heat is extracted from the heat source? And C. What heat is delivered to the cold reservoir? I'm going to sketch a heat engine diagram showing the flows of energy, and then let's solve the problem. Summarized here is the information given to me in the problem. I have my heat flow diagram with 500 joules of work coming out of the engine. There's an efficiency of 0.45 and the cool exhaust temperature is 513 kelvins. Part A. What is the temperature of the heat source? Since they tell me I have a Carnot efficiency, then I can use the Carnot equation that relates the efficiency with the temperatures. Now I want to solve that equation for TH. So the first thing I'm going to do is to subtract the efficiency from both sides and add the fraction to both sides. Now I'm going to multiply both sides by TH. And now divide by the parentheses and put in the numbers. I find that heat is flowing into the engine at a temperature of just over 930 Kelvin. B. What heat is extracted from the heat source? Well, if I know the work and I know the efficiency, I can figure out what QH is. Let me solve that equation for QH and put in the numbers. I get just over 1100 joules flows into the engine. Now, if I've got 1100 joules flowing in and 500 comes out, then 1100 minus 500 is going to be the amount that goes out into the environment. Let's solve for that. So I started with the conservation of energy, and now what I need to do is to put in the numbers. I get just over 610 joules is dumped in the atmosphere. So to review this lesson, we have talked about heat engines. This diagram that we're drawing is going to be important. We've discussed efficiency, and we've talked about Carnot's ideal engines, in which the ratio of the heats can be given by the ratio of the temperatures. The change in entropy for the cycle of such an engine is going to be 0. There are no changes in entropy for an ideal engine. So for now, that's it.